Okay, section 3.6, marginals and differentials. So we've been talking about marginals for a little bit. I've been sneaking them in here and there, and I've been kind of guiding you with them. But we have three things to talk about. The marginals for cost, revenue, and profit. And differentials is our second topic. Now these two things are very, very linked. They're almost the same, which is why we cover them in the same section. And the third thing, which I realize now in these packets didn't make it, is approximations / linearizations. Now the nice thing is if you're doing differentials, you're doing linearizations or approximations anyway. So we'll just, at the end, at the last page on the back, but talk about the formula when it asks for specifically a linearization. Good news is you've already done linearization a bunch of times. So marginal cost, marginal revenue, marginal profit. So we have our cost function C of x, revenue R of x, and profit P of x. These are total cost, revenue, and profit from selling x items. The marginal cost at x is given by the derivative C prime, and it's the approximate cost of the x plus 1th item. So if you find C prime of 30, you're finding the cost of producing the 31st item. And the way that we think about this is given by this. So C prime of x is approximately the same as C of x plus 1 minus C of x. So it's not the total cost of producing x plus 1 items, it's the specific cost of that x plus 1th item. So you take your total cost after x plus 1, you subtract away your total cost after x items, and that's approximately what the marginal cost gives you. Marginal revenue and marginal profit are the same. They give you the revenue of the x plus 1th item and the profit of the x plus 1th item. So the same thing applies. R prime of x is approximately R of x plus 1 minus R of x, and P prime of x is approximately P of x plus 1 minus P of x. Now, it's not perfect. That's why we use the approximate symbols. There is some difference, but if you think of it this way, this will help you remember what these three functions are made for. So let's take a look at an example here, calculating marginal profit, revenue, and cost. So total profit in part A, given our cost and revenue functions here. So this is 62x squared plus 27,500. And this is x cubed minus 12x squared plus 40x plus 10. So total profit, R minus C. So that's x cubed minus 12x squared plus 40x plus 10 minus 62x squared plus 27,500. And this means that our profit function P of x is going to be x cubed minus 74x squared plus 40x minus 490. So now in part B, we want the total cost, revenue, and profit from production of 50 units. So we want P of 50, R of 50, and C of 50. So R of 50, 50 cubed minus 12 times 50 squared plus 40 times 50 plus 10. And when you plug that into a calculator, you get $97,010. The cost of producing 50 is 62 times 50 squared plus 27,500. And when you plug that in, we get $182,500. And the reason I save profit for last is because, yes, you could plug it into this function, but since profit is just revenue minus cost, we can also just do R of 50 minus C of 50. So 97,010 minus 182,500. And when you do that, you get negative 85,490. And so anytime you're asked to calculate something like this, you should think about, what does this mean? So having a negative profit means that we're losing money. We haven't started making money yet, which means we haven't recouped our losses. So this company, whatever they're making, you definitely don't want to only make 50. You need to make a whole lot more than 50. Based on this, I would guess, around 100 would be a good choice. Now, the way that companies use marginal functions is to try and figure out exactly what that would be. So we want the marginal cost, revenue, and profit. So C prime of x would be 124x. R prime of x would be 3x squared minus 24x plus 40. And P prime of x is R prime of x minus C prime, or we can take the derivative directly. In either case, we get 3x squared minus 148x plus 40. So we have our marginal functions, and now we want C prime of 50, 124 times 50, and this equals $6,200. So this means it's going to cost $6,200 to produce the 51st item. R prime of 50, plugging 50 into this, what is that? 3 times 50 squared minus 24 times 50 plus 40, and plugging that into the calculator, we get $6,340. And again, this is the revenue from selling the 51st item. So you can already see, if we go now to our marginal profit at 50, this is R prime of 50 minus C prime of 50, and that's going to be $140. And this is positive. So that's all this question asks. But as usual, I want to talk about what the implications are, since this is a real-world problem. So you have a net positive profit, marginal profit. That means that the 51st item is making money. So we should keep producing and keep selling. Because now the company's actually making money. So they made their first 50, they projected their first 50, they're going to lose 85 grand. But on the 51st item, they're going to start making money. And if you did P prime of 51, P prime of 52, P prime of 53, this would keep going up and up and up. Now we know where this is going to hit its maximum. It's going to hit its maximum at the critical value, where our P prime is 0. So eventually it'll get higher and higher and higher, and then it will slow down and decrease again until you hit 0. So if we turn the page here, we'll just have a little bit more discussion about marginals. So oftentimes in business, a formula for C, R, and P don't exist. When they don't exist, the marginal profits, costs, and revenues are extremely important. And we can, by knowing the cost of an item and the marginal cost, we can make a reasonable prediction for the cost of the next. So in example 1 that we just did, formulas do exist, so it's possible to see how accurate our predictions are. So we predicted C prime of 50. This was 6,200. That's what we calculated. And we said C prime of 50 in our definition should be approximately C of 51 minus C of 50. So this is the actual cost of the 51st item. And so when we plug this in, that's just plugging in our formulas, we get 62. So this is the estimated cost and this is the actual cost. And this is both of the 51st item. Actual cost for the 51st item. So you can see the marginal functions are approximations. They approximate what that actual cost is. And it's useful because you don't need to know the functions, right? So sometimes if you're producing something that's really complicated, you need some stuff from this company, some stuff from this company, some stuff from this company, and you're buying all this material or items or labor, and you put it all together. You know what your total cost was. You know how much it cost you. You probably wouldn't be looking at 51 and 50, but maybe you're looking at the first 100 units and then the second 100 units. You know what that cost was. And so you can adjust and figure out what your marginal cost was on average. And then you can use that to figure out how much each individual unit was actually costing you. And if you have that, then you can guess, should I keep producing after this, the second 100 units, you've made 200 total, should I keep producing things, or is this never going to change? Have I already hit the maximum? And you can use marginals to do that. Now in mathematics, we want to do this for all types of functions, and so that's where differentials comes in. So here we have differentials in delta notation. So like I said, we don't always have consecutive numbers like this. When we don't, we just need two values. So if we know x equals a and x equals b, then we set h to equal b minus a and approximate y equals f of a using our derivative f prime of a can be approximated by f of a plus h minus f of a, and that means that f prime of x can be approximated by f of x plus h minus f of x. So this is almost our difference quotient. Right? Our difference quotient for the definition of the derivative is dividing by h here and taking the limit. So that's why it's only an approximate for that marginal. Our differential that we're building is going to be approximate. It's not going to be exact, but it's going to be close enough. So the change in y over the change in x, delta y over delta x. This can be approximated by f of x plus delta x minus f of x. And what this means, change in y, remember, delta y is f of b minus f of a, and delta x is the h, it's our change in x. Well, this means that we can solve for delta y, and we know that delta y is going to be f prime of x times delta x, because we can solve using this equation and this equation. We can reduce it to this equation. Now this is really important because as h gets very small, so as h approaches 0, we have delta y becomes dy, and delta x becomes dx. And these are what we call the differentials. So the differential in y and the differential in x. For y equals f of x, we define dx is the differential of x, and we say dx equals delta x, or it equals h. It's that change, doesn't matter. And dy is the differential of y, and dy, using this notation, as h goes to 0, delta y becomes dy, delta x becomes dx. dy is f prime of x dx. And you can kind of see where we get this from, because we know that f prime of x equals dy over dx. We said that these were one and the same. The derivative of y with respect to x is f prime of x. So this is where we're getting this. And that's where it comes from. So we can illustrate dx and dy. It's not to the right anymore. It's below. I changed the format. So note that dx is still delta x, but dy is not equal to delta y. Though you can fudge it a little bit, and you can say, as I've written here, dy is approximately, delta y. It's close, right? Just like up here, this is close to this, but it's not actually equal. They're slightly off. And the smaller the change in x, the more off your differential dy will be, the more off your marginal will be. So you can kind of get the idea here. If you look at our function, this line is our tangent line to this point right here. And we know its slope is f prime of x. And it's got, from here to here, this tiny little delta x. So now if we're approximating this values, we know that dy is going to change. And specifically, you can see the difference. Dy misses this chunk off of delta y. So we're looking at from this point to this point here, and we're using the tangent line at this point. So you can think of this x value. This is the tangent line. If we make this x equals a, this is at a. So we're using that tangent line to approximate what this value would be up here. Now you can see we do miss because we have space here. And as I said, as the dx, or the delta x, that affects it. So as this delta x gets smaller, this tangent line is going to teeter and it's not going to move, but our delta y from here to here will grow or shrink. So as delta x gets bigger, you can see I drew these lines here. The difference between the function and our tangent line that we have right here gets larger. So as you get further away from the point that you're using to approximate, the a value, your approximation, your differential, becomes less accurate. So for marginals, we use one right after the other because that's like saying x equals a and then x equals a plus 1 right there. There's not a lot of difference in between this line, and if you have the paper in front of you, you see there's barely a gap there. But as we get further away from that, our approximation, our tangent line, is further and further from the function. So there's a certain window in which we can use that. But our differential can be recalculated. So let's say now I want to calculate here. I don't want to use this point anymore. I can recalculate and make a new tangent line and use that. And that's the beauty of how we define our differential, is it's entirely dependent on x. And that x is where we start. So if I wanted to use this tangent line, I would no longer use the approximation over here. I'd use the approximation up here. And I'd recalculate and I'd say, okay, this is x equals b. And I would use b in here instead, because it would make my approximation, my differential, that much more accurate. So that's kind of a lot of theory there. Let's flip this over and take a look at some actual problems where we're actually using differentials. So in this first example, we have the function y equals f of x equals the square root of x, and we want to find dy. So dy is f prime of x dx. So this is, we need to find the derivative. F prime of x is 1/2 x to the negative 1/2. So dy is 1/2 x to the negative 1/2 dx. So this is what we call the general differential. Because we don't have any y's or x's in there yet. We just have it in general. So now in part B, we're going to calculate the value of dy when x is 9 and dx is 0.1. So that means we have dy equals 1/2 times 9 to the negative 1/2 times 0.1. Well, this is 1/2 times 1/3 times 1/10, which equals 1/60. So what this says is as x changes or goes from 9 to 9.1, because that was our change in x, our dx, y goes up 1/60 from whatever its value was. So notice we don't have to know what that value is to start. We just have to know what our initial starting point was and how much we changed by. So if we go back to marginals for a second here, if we have 100 units and we know the differential, the general marginal function, well, we know the change. 100 to 200 has a change of 100. So we could plug those in and figure out what that approximate change was. So in part C now, we're going to compare our results. So calculate the value for square root of y, for delta y over the interval 9 to 9.1, and compare the results to part B. So delta y from the previous page we know is f of b minus f of a. And so delta y is f of 9.1 minus f of 9. And so I've done this in the calculator. This is square root of 9.1 minus square root of 9. And this is going to equal 0.01662. And our dy, we said it was 1/60th. And if you plug this into your calculator, it's 0.01666 repeating, so 67. So now we can compare the actual change in y to the approximated change in y. We're pretty dang close. We're off by 0.00005, which is really good. So if you want to know the difference, just subtract 0.01667 minus 0.01662. This is 0.0001234.5. Or as a percentage, this is 0.005% off. So if you were trying to estimate values for money, let's say, and you could get within 5/1000ths of a percent, you'd be pretty happy with that estimate, which is why we use the differential, because it's an extremely accurate estimate. Very, very useful. Excuse me. So, one more thing to say here. With this differential calculation, you can use this to calculate things a little bit easier. So I'll do this over here. Since we know dy is 1/60th, and we're going from 9 to 9.1, you can use this to approximate f of 9.1 is about 3 plus 1 over 60. And then you can check this, so you know this is supposed to be the square root of 9.1 as 3 plus 1 over 60. So in your calculator, plug in square root of 9.1, write it down, and then in your calculator, do this and see how close you are. You'll be pleasantly surprised with how accurate these differentials actually are. So, in the next example now, this is a tile company, and so prepping new tile, Michelle measures the floor of a banquet hall and finds it to be square, measuring 100 feet by 100 feet. Suppose these measurements are accurate to plus or minus 6 inches. This is the tolerance. In part A, we're going to use a differential to estimate the difference in area. This is an approximation problem, so this falls into that third category. This is approximation. And it's due to the tolerance. So when you measure something, usually you're told, this is plus or minus 6. Usually you're told, oh, it's 12 feet plus or minus 2 inches or something like that, meaning that there's an error associated with your measuring device. And if there's an error with that measuring device, that means that there's an error with what you're going to calculate to be area in this case. So if we look at differentials this way, area equals side squared for a square. So that means that dA, ds, the change in area with respect to the side, is going to be 2s. And then you can solve, quote unquote, solve dA is 2s ds. This is our differential for the area. This part here, that's our tolerance. So that means that dA equals 2 times 100 times 6. Now remember, your tolerance could be off in either direction. So we really use the absolute value. Absolute value of -6 equals the absolute value of 6. Because if we're off by 6 inches in either direction, this will be okay. Now remember, units are important here. So this is in feet and this is in inches. So I'm going to rewrite this as 2 times 100. 6 inches is 1/2 a foot. So this is 100 feet squared. So that means our error is 100 feet squared. So we could be off plus or minus 100 feet squared. Now if you think, oh, that's a big error. Well, this is an enormous room. It's 100 by 100, or 10,000 square feet. So if you're at 10,000 square feet and you're only off by 100 feet squared, that's really not that bad. So part B says compare the result for part A, with the actual difference in area delta A. So remember, delta A is A of 100 plus or minus 1/2 minus A of 100. So that means we need two calculations. We need the plus and the minus. So this is 100.5, A of 100.5 minus A of 100, or A of 99.5 minus A of 100. So this is 100.5 squared minus 100 squared, and this is 99.5 squared minus 100 squared. And this is 100.25 feet squared when all said and done. And this is negative 99.75 feet squared. So now you can compare these to our approximate error. We could be off as much as 0.25 or as little as 0.25 in either direction. So our differential is only 1/4 of a foot off the actual difference in either direction. So if we're under by 6 inches, that means that we're under by 1/4 of a foot in our approximation, in our error. And if we're over by 6 inches, we're over by over by 1/4 of a foot. So in either case, if you tell someone, yeah, it's about 100 square feet, they're going to say, sure, yeah, of course. You're 1/4 of a foot off in either direction. So again, this is just reiterating how accurate the differential is as an estimator, as an approximator. So in part C here, if each tile covers 1 square foot and a box of 12 tiles costs $24, how many extra boxes of tiles should Michelle buy for covering the floor? And what is the extra cost? Well, we don't know what direction we're off by. So if you're the contractor here and you're thinking about, well, should I buy, what kind of tile should I buy? Well, we need to take the maximum error. So we always want to account for the maximum error. So what we're really looking at is, since we know the tolerance was 6 inches, we're looking at if S is 100.5 or S is 99.5, right? 1/2 foot off in either direction. Well, if S is 100.5, our area would be 100.5 squared, or our area would be 99.5 squared. Well, this is certainly larger. So we want to use this value, because if it turns out to be this and we've accounted for this much error, well, great. We have an extra square foot than what we needed. But if we do this one, and it turns out that this was the error, well, now we're not going to have enough tile. So we always choose the maximal error. So this means our area will be 10,100 square feet. And we need tiles to cover this much. So we can only buy them in boxes of 12. So we take 10,100 and divide it by 12. Because each tile covers 1 square foot, we get 12 tiles per box. So we divide this by 12, and this is 841.67, approximately. So we can't buy 841.67. So we're going to buy 842 boxes. So now this is how many we're going to buy. And I've run out of space here, so I'm just going to flip this over. So we're buying 842 boxes. The cost for 842 boxes will be 24 times 842. Now this is going to equal some dollar amount. I don't actually care what that number is, because what we care about is the change, is the difference in cost. So, paper. Remember, it asks, how many extra boxes of tiles should Michelle buy? Well, we know the extra boxes, or we know the total boxes to account for the maximum error. And we want to know what the extra is. So if we're thinking about extra, to calculate extra, well, assume no error. That is that the S is perfectly 100. So A is perfectly 10,000 feet squared, and we would do 10,000 divided by 12, just like we did. And this comes out to be about 833.33. We obviously can't buy 1/3 of a box, so we buy 834 boxes. This is how much you would be buying no matter what. So now you do 842 minus 834, which is 8 extra boxes. So you're buying 8 extra boxes. Now I don't need to do this calculation. So I do 8 times 24, and that's $192 extra. And that's how we figure out the extra cost in extra boxes. So you always look at your maximal error, what that could be, compared to if you had no error. And you don't always need to calculate everything for that maximal error, because you're really thinking about the difference, which is what we're doing here. So the last little thing, 5 minutes here to tidy up, is linearizations. So differentials encompasses approximations, but sometimes we can be asked for a linearization, which is a linear approximation. Approximation. So if y equals f of x, and we want to approximate f of a, we do a couple things. Number one, choose a b that's approximately a. So what you're going to find is a is usually going to be a decimal. So the 2 problems ago, we were doing square root of 9.1. Right? We would approximate that by square rooting 9 instead. So you pick this, and you want b to be a whole number. Well, then the linearization, which we call capital L of x, is f prime of a, or f prime of b, times x minus b plus f of b. So this is the linear approximation. And then you can approximate L of a as f prime of b times a minus b plus f of b. So I said you've already done linearizations, because what it turns out this is essentially the tangent line. At x equals b. So I'm not going to do any problems with linearization because we've been doing tangent lines all semester since we introduced derivatives. Almost every couple sections I say make sure you can calculate the tangent line. So if you're going to do a linearization or a linear approximation, a differential is close to a linear approximation. You just construct the tangent line at x equals b, and then you plug in a. You just pick your b so that it's really, really close to a, and you make b a whole number, because like I said, a is most likely going to be a decimal. So that is the end of 3.6.